Welcome back, engineers. We are discussing architectural styles, and in this video let's look at an interesting one, which is space-based architectural style. So this architectural style actually promises infinite scale. Can you imagine? I hope you're ready. Let's get started. So before we get into the details of this architecture style, let's have a quick story. Okay, let's say we are at a not so awesome library this time. Okay, this is a library which is not so great. Let's see why. So in this library, there are people who want to get their books issued. They just want to check if something is available or not. And for this, they go to the librarian. Librarian is taking a request from one user and checking if that book is available in a long list of catalog, right? Let's say this is the catalog. So for each request, the librarian has to check through the entire list of books to see if something is available or not and then respond back to the user. Okay, and if there are more number of users, the number of people in the queue is always increasing, right? So this is not a good situation to be in, and the librarian is actually constrained by the size of this catalog, right? The bigger the catalog, the more books we have to evaluate to find the book that we need, to check the status, or even to issue the book to the customer and so on, right? So this becomes a big constraint, the catalog itself, right? And also the fact that there is only one librarian. This is also a constraint. If we have multiple librarians, they can all connect to this catalog and check it and then respond in parallel, right? So that is something we can do. But at this stage, this is not so awesome library and users are not satisfied, right? Not a good position to be in. So let's enhance this a little bit. We'll make it into an awesome library. So what do we do? Awesome library, we will address the two bottlenecks that we saw before. First is that there was only one librarian. So instead of one librarian, we will add multiple librarians, right? So every librarian is addressing different set of customers and they are all talking to different librarians. And other bottleneck that we saw before was a huge catalog of books, right? So that was a big constraint because everybody needed to go to the same catalog and then refer to it for the current status. But instead of that, if you look at the diagram here, every librarian is having an iPad. Let's say a small iPad, and that is given individually to each of the librarians, and each iPad contains a current state of the catalog, right? So each iPad can quickly scan through the current state of the catalog and issue a book, check status and whatever, and if there is any change, each iPad is updated against each other so that everybody is on the same page like this, and the requests are processed in parallel, right? So this type of situation is actually sounding great because now we have multiple librarians, which means we kind of did some kind of load balancing, right? So some users can go here, some users can go here, and so on, and each of them have their own little libraries, the catalogs, so that the check is not restricted to some global catalog, right? So it all sounds fancy, and this is what this architecture also talks about, but it all comes down to some complexities and cost as well, right? So if we look at it from a high level perspective, this can be scaled to any number of librarians, right? I can keep on adding librarians as my customers grow. I can reduce the number of librarians as my customers shrink, right? So that gives us potential scale, and it also removes a bottleneck from the main catalog, which is, you can say, as a database, right? But in order to implement this, we need some complex coordination between all these librarians. Everybody should be on the same page. Everybody should be able to access data instantly and also should be able to update instantly. What if the new librarian comes? Who's going to provide the new librarian with the latest iPad, with the latest info? Who is going to shut them down? And there can be many such questions, right? So those are the trade-offs that we'll need to evaluate. But on the paper, this provides infinite scale, right? Now this was an example from a non-tech world, just to help you understand the concept. Let's try to get slightly deeper into the tech world, right? So we generally see this pattern in most of the web applications, right? So there is a user is accessing some kind of a browser. From the browser, we're making a request to the front-end server. The front-end server makes a request to the back-end server. Back-end server accesses the data from the database and then returns back to the user, all the way back to the user, right? So this is how typical web applications work, right? So if more number of users have started to use our application, more hits are coming to our front-end server. Maybe it is experiencing some kind of a crunch. So we will add more front-end servers here, right? And maybe put a load balancer in front of it, right? We can do that. And let's say our backend server is getting crushed. We can add more backend servers, right? So this is something that we can do independently because these are stateless machines, right? But we cannot do the same thing with database, right? So once you start using multiple servers for a database, you start to go into the region of distributed databases, distributed data partitioning, data replication, and so on, right? So this is a situation that is quite complex in nature, right? Can we do something at this end of the spectrum? Can we do something at this end of the spectrum so that we still get good scalability and not touch the database at all, or touch it without having any impact on scale at all, right? Can we do that? So this architecture provides us an approach to do that. Now let's see how the architecture actually looks like. So the architecture actually looks quite complex because there are a lot of moving parts, but the concept is actually pretty simple. Instead of accessing everything from a database, you put stuff in RAM, in memory, and then access it from there. And that is the core concept of this whole architecture style. Okay, let's see how it goes. So at the end of it, we have the database where our actual data resides, but we don't want to access it for every user request, right? So what we do, whatever is our processing unit, the application servers, the backend application servers, so we give it an in-memory data grid. So this piece here, in-memory data grid, right? So whatever data we want from the database, we just put it here up ahead so that processing unit can instantly access it in memory, right? And we can spin up multiple such processing units. This is 1, this is 2, this is 3, right? We can keep on increasing processing units depending on the user load. If there is more load, we add processing units. If there is less load, we remove processing units, right? And every processing unit has its own in-memory data grid cache, right? That's all we need. We need data in memory, instantly accessible, super fast, super performant, and then we just use it to answer our user requests, right? Very fast. But even though this sounds really simple, in-memory caching is actually quite complex implementation because now there are multiple processing units involved. Each of the processing units can also modify the data, and we need to keep all the units in sync, right? So how do we do that? We use a middleware. So this virtualized middleware that you are seeing here has multiple things. Let's go over them one by one. So first is a messaging grid. So this acts like a load balancer. Okay. Now, because we have multiple processing units, user will be requesting through this messaging grid, and the messaging grid will decide which processing unit will actually handle the request. So this can be a simple round robin algorithm or a complex implementation, but the idea is to distribute the data among multiple processing units, right? So that is the purpose of this messaging grid. And then we have the data grid. This is responsible for keeping everybody in sync, right? So if something is changing in the memory grid from processing unit 1, who will tell processing unit 2? Because processing unit 1 is not aware of processing unit 2, processing unit 2 is not aware of processing unit 3, and so on. So there should be some central manager who's keeping everybody in sync, and that is the responsibility of this guy, right? So this system will take care of replicating changes across processing units. And then the third piece is processing grid. This is an optional one. So what this does is, if there is any coordination required between multiple processing units, this can be delegated to this guy. So this is like an orchestrator. So this processing grid is an optional one if only when we require coordination among different processing units to handle one request, let's say, right? And the fourth one is the deployment manager, responsible for spinning up and down the processing units. So deployment manager is monitoring the user load at this point of time. If there is more load, we add more processing units. If there is less load, the processing units can be compressed, right? So that is the job of the deployment manager. So these are some of the moving parts. Now, there are some open questions remaining. How do we keep the database updated, right? At the end of the day, database should be the single source of truth, right? So for that, we have something called as data pumps. Data pumps, okay? So whenever there is a change from any of the processing units, not only is the data grid updated, data pump is also accessed through event queues, and these data pumps actually do data reading and data writing. So when do we do data writing? So whenever there is a change in one of the memory grids, it is synced across different processing units anyway with the help of data grid, but it is also sent to a data pump event. This can be a messaging queue, message broker, and whatever. And this data pump event is passed on to a data writer. Data writer will update the database, right? And similarly, whenever there is a new processing unit 4, let's say, that is required, somebody needs to give this processing unit 4 the current state of the database, right? So that is the purpose of a data reader. So this data reader will give out all the information that is required to spin up this new processing unit, right? So those are the moving parts in this whole architecture. So a quick summary about what we just learned about. So there is a processing unit, which is nothing but an application server, which has an in-memory data grid and multiple subcomponents. So it is accessing data from the in-memory data grid instead of the main database. And because of this, we are achieving super fast performance and also scale, because we can spin up multiple such processing units depending on the load of the requests, right? And then there is a virtualized middleware. This middleware has multiple components, messaging grid acting as a load balancer to distribute load among different processing units. And then we have data grid, which is taking care of sync between the memory grids, right? And then we have a processing grid, which is an optional one, which is an orchestrator if something is required to be coordinated between the different processing units. And then we have a deployment manager, who is obviously responsible for spinning up and down these units, right? And finally, to keep database updated, we have data writer, which is taking data pump events from individual processing units. And then we have data reader, who is responsible for giving out the current state of the database whenever there is a new spin up of a processing unit, right? So the architecture looks complex, and it is actually complex to implement it, but the fundamental concept is really simple, right? So to remove the constraint from the main database, so that we don't have to scale the data layer, but we can do some stuff at the application layer level, so that we can get some good scalability, right? So those are the features of this architecture style. So we have discussed all these components: processing unit, in-memory data grid, messaging grid, data grid, processing grid, deployment manager, data pumps, data reader and writer, right? So these are the components. Now let's see the trade-offs. Like I said, we can get good scalability because of this. We can spin up any number of processing units. We get good elasticity. Elasticity is nothing but sudden bursts of traffic. Maybe some concert is announced, maybe some event that goes on sale at midnight or something like that, right? So we expect a lot of load at that point of time. So we can make use of this architecture. We get good performance as well, because reading stuff from memory is super fast. We have already discussed this in latency video, right? Definitely check it out if you haven't done already. You can see it here. It's in nanoseconds for looking up in memory versus disk, right? So definitely check it out if you haven't done already. So these are the good stuff. What are the cons? This is expensive, because RAM is expensive and it's volatile. RAM versus disk, RAM always wins in terms of performance, but it is really expensive, right? So as a quick exercise, why don't you just check out the price difference between, let's say, 1 GB of RAM versus 1 GB of disk, right? Let's see what's the price difference. And the other cons are, it comes with a lot of complexity, because we need to manage all the coordination between all the processing units, in-memory data grids, load balancing and all that. So a lot of complexity is added. We also have challenges in testability, because we need to have the right setup to test this at scale. We need to have the spinned up instances. We need to have that deployment manager up and running to see if something is getting spinned up on the fly when the user load is increased, and it is getting spinned down when the user load is decreased, and so on. So this is a challenge to actually do testability, but we get these benefits by doing this, right? So those are the trade-offs for this architecture, guys. Let me know if you have any doubts. I hope you learned something new. If you did, definitely please leave a like. And if you have any questions, definitely let me know in the comment below. Thank you so much for watching. Please subscribe if you haven't done already. I will see you in the next one. Cheers.